Okay, so now we're going to pick right up where we left off above. If you restarted this notebook, be sure to go back and rework the cells above because we need to be able to load the appropriate libraries. But we can just jump right in, and here, and also the data. And here we're gonna do same thing we did before. We had lin_df, which are linear regression data frame. And now we're going to do a class or a classifier data frame. And we're going to get it again from that process table data frame that we created up there. I'm going to keep everything from that table except for yesterday's high. Actually, I'm going to get rid of yesterday's high. And that's because I think maybe these other things are going to be useful for our actual determination of whether or not school is closed. So now we're not going to use it. We're not trying to predict today's temperature based upon yesterday's temperature or tomorrow's temperature based upon today's temperature, however you want to think about it. We're now going to get back to our original goal, which was predicting whether or not school was closed based upon these features here, namely the precipitation, the accumulation, the minimum temperature, the maximum temperature, and the maximum wind gust for the day. We have a link back out here to our friend confusion matrix that we've talked about before, and we're going to load a bunch of libraries. Don't worry about all this code here. This is something I wrote just so that we could go ahead and we could look at things. And I sort of said whether or not a model is good or not. I sort of made a pass-fail based upon a set of different success metrics. We'll talk about what those are just below. It is important that you run these cells though, because they're going to be the thing that load that into the memory so we can access it. So here we have our data frame for class TF. And here we'll go ahead, we load those. Now those are accessible. This is a function I made that's accessible in some libraries. And now we're going to go ahead and do something very similar to what we did above. We have our class data frame, and we want to split it just like we did above into holdout data and training data. And so testing and training data. And so we'll do the same code exactly as above. 20% fraction, put it into holdout. Take everything that's not in that 20% holdout and create a new data frame that's going to be our training. And then this is a tricky thing here. We actually need to drop from the features. We're not getting the features. The features is everything but the target, right? So this is we're dropping the thing that has the target in it. And then the labels or the target is just that one column, the closed column. And then we do the same thing. This is our training data. We do the same thing for our test data. So we've just done the same thing we did above, which is that we created a list of training and testing data that we're going to be able to use. And here I go ahead and I print out the size of the training data. And then actually this little bit of code here tells me about the counts, sort of ones versus zeros, so we can just read a feeling. So the training data, there's 588 rows. So we're looking at 588 days worth of data. 576 of those days, school was open. 12 of those days, school was closed. Right, so remember, we keep talking about keeping ourselves honest. And we keep using this example. We say, well, you could be 98% accurate by just saying school is open. That could be your model, right? It could be 98% accurate and school is open. So this is sort of keeps us honest. This goes back to, this is the percentage overall. Overall, there were 722 days where school was open and 13 where school was closed. So this gives you that sort of look at the overall data, so including our testing and training. So again, we want to beat 98%, otherwise we're just doing the same as always guessing school is open. What we're going to do now is we're going to take our data, we've prepared it, the major preparation in the previous level by turning it all into these nice numbers and these nice tables. And we're just going to take that and we're going to feed it into a set of algorithms. And we're going to see how they can do at predicting things. So we have this logistic regression. We've talked about logistic regression in the video above and in previous classes. So I'm not going to go into its operation here. But basically what we're doing is we're loading the model, or we're loading the library. We're then using logistic regression. We give it some parameters. So it's from establishes a model. And then we're going to give it our training data, our features and our labels. And we're going to do that same fit. You'll see the syntax here is the same as the second the second regression above, because it's the same as the scikit-learn set of packages. That syntax is the same. We're going to predict things again. We're going to use that same predict feature we saw up above, and we're going to make some predictions. Here, these predictions are going to be just predictions is either going to be 0 or 1 for no or yes. The probability is going to actually be a value between 0 and 1 for its probability of it being either, well, the probability of it being a yes. So if it's 1, then it's 100% probable it's going to be yes. It's 0.2, it's only 20% probable that it's going to be yes. And then we just put out the name logistic regression, and then I use this evaluate function that I created above, and we'll see what that does. So we get some errors. The reason we're getting some errors is because the number of examples, the number of positive examples we had of time school was closed was so small that we actually couldn't calculate all of the values here. So precision, you remember, is one of our success metrics. And this is basically happening because one of those measures that you go into making up precision was a 0, and you're dividing by 0, and so you're getting this number. And you can see, if you look at this here, we had no true positives, and 1 false negative. Then we have 146 true negatives. So there aren't a lot of potential yeses to get right here. And you know, so that you know makes it clear that we don't really maybe have enough data to do a good model. But I think we already knew that, because I always keep talking about this as the crap example model. But let's see how we can know that. Here are some of those success metrics we talked about. So accuracy, our model was 99% accurate. Well, that's really great. The thing is, if we look at the zeros compared to the ones, well, 99% of the training data, remember, this is not all the data, this is the data that was not in our holdout data. And so what we could do actually is we could go up and we could redo that sample again. That's done randomly, so we get slightly different answers, and we'll do that actually in a second. But the point is here, for this particular draw, out of the data, 99% of the time school was open, only 1% of the time school was closed. So even though our accuracy is 99%, it does not beat the naive model where you just always say school was open. Some things that we know before, we know about recall and precision. Precision is the one that there's not enough data to actually calculate it. Recall 0, we're not catching any of the actual yeses in the data, so it's pretty horrible. And our F1 score, which you'll remember is a weighted average of these two guys, of recall and precision, again is not a number because there's no precision, so it can't figure out the F1 score either. I want to talk about some of these graphs and some of these other things. So here, obviously, we saw the true positives, true negatives, false positives, false negatives. So this we could use to make a confusion matrix. But there's this new thing here, AUC. It's the area under the curve. That's the area under what's called the ROC curve, the receiver operator curve. So it's the area under this line here. And the closer that is to 1, the better it is. And what this graph is showing is it's showing us the false positives versus the true positives, their rates, the rates of the false positive versus the rates of the true positives for different thresholds, different cutoff thresholds. So if you think about this classifier, remember it can either say, yes, close school, or no, don't close school, or it could give us sort of that probabilistic distribution we talked about. It can go, oh, there's a 20% chance they should close schools, or a 70% chance to close schools. Well, you could decide that you only want to say close school when the classifier gets above 90%, okay? Or you could just do the default, which is anytime it's above 50%, and we're going to say it. What this is doing is this is graphing the false positive rate and the true positive rate for every threshold that you might consider in the cutoff. And so as you, and it's important to realize that on this graph, you don't see what those thresholds are. This is the consequence of graphing the rates at every one of those thresholds. So, somewhere on here is if that threshold's down at 0, right? So if the threshold's down at 0, you're not going to have any false positives because you're not. Or I'm sorry, you're going to have all false positives because everything's going to be a positive if your threshold is down at 0. And as you move to 50%, you're going to start having different behavior. And so basically, you're plotting every one of those points for all of those values, and that's making this. Because this is this really weird situation where we didn't really have a lot of data, not even enough to do these other things. This looks unrealistically good. So this is looking basically like a perfect ROC curve, but in reality, it's not. And again, this comes back to the idea that some metrics are not the right metrics. So that's why we look at different metrics. So again, accuracy, we talked about why that isn't a good metric all the time. And that's why you look at these things together. So we've got the ROC curve here. We've got the precision recall curve. It's similar in that it's plotting out points on here for every different threshold that you could use as a cutoff to say, yay, close school, don't close school. And you can see here that it's changing over time. And here we're plotting the precision versus the recall, right? So we've heard about those before, and so that information is captured there. This AUC, in case I didn't mention it or make it very clear, that's the area under this curve. So basically, if it goes all the way like this, then the area under this is everything. So it's 100% of the area. So you want an AOC very close to 1, just like you want an accuracy very close to 1, an F1 score close to 1, or recall or precision close to 1. So the idea is if you saw 1, 1, 1, 1 across all these, then you have a perfect classifier. And so these are nice to sort of show you some of how things are behaving at different thresholds. And then I just did a predictions versus reality graph, which was just something I threw in for myself. I wanted to see what was the distribution of predictions from my classifier looking like versus the actual reality. And here you can see that things are really imbalanced, right? So the true values are in blue. So to say most of the days were 0, which is keep school open, and only a very small number were closed school. And you can see our predictor, it mostly just said no all the time, but occasionally it said, oh, no, but it was sort of half-hearted in its no. It wasn't 100% no. It was, a little here. And so we can see how that behaved there. I said you get different results if you got a different random draw, right? So we can just go back up here, do exactly that, get a different random draw. So there you go. Now we had 579 and 9. And you'll remember up above, there were 12 in the training data that where school was closed, which meant out of the 13 total, there's only one actual positive we were going to be able to have in our holdout data when we did the testing. So this is a much sort of more reasonable draw. This won't change because this is based on the base data. But now this is going to change because now we have different training data, right? So now we have 9 positives as opposed to 12, which means that we now also have more in the testing data to test against. So if I run this, okay, now here we got really, really lucky, or at least in some respects we did. We got a true positive, and we got a lot of true negatives. We got 0 false positives and 3 false negatives. And so that actually means that our precision was really good. So our precision was perfect. Every time we said something, school was closed, school was closed. But our recall wasn't so great, okay? Our recall was actually kind of crap. Only 25% of the time do we actually find those closed days. So that's our false negatives there. Those are things we called negatives, but should have been positives. And so again, you can see the accuracy looks good. Here the AUC looks good, but obviously the F1 the score doesn't look good because the recall is no good. And so here you can see, you look at this at first, you're like, whoa, we're doing great. But then you realize we did great. Everything we said was a closed day was a closed day, but we didn't catch most of the closed days. So, so not so great. And so that's why this failed here. In order to pass, I said that you had to do better than sort of always guessing that school is closed. So your accuracy has to beat the sort of naive accuracy of always guessing no. Your AUC, if it was just random, if your classification was random, that would come to be about 0.5. So your AUC needs to be north of 0.5. And similarly, for your F1 score, your recall and your precision, those need to be north of 0.5 in order for you to pass. So this did not pass. So the question is, can one of our other algorithms do a better job at predicting? So this was using our logistic regression. Here we're going to use a decision tree. And this decision tree is exactly what it sounds like. It's a flow chart. It says, if this value is bigger than this, then ask this next question, was this bigger than this? And you can get a decision tree and sort of see how that works. What's nice about this is you actually can visualize this. So I'm going to go ahead and run this here. And then here it's actually telling me this is what it came up with as the decision tree that worked best for this training data. And so it said basically, if the accumulation was greater than 3 inches, then I go over here because this is accumulation less than 3, true. So if accumulation less than 3 is not true, then that's to say that it is greater than 3.79. So over here, and the mix of that is 7 closed to 3 opens when I get into this. Here we start off with 579 opens and 9 closures. But if the accumulation, so if we have almost 4 inches of snow, odds are that means we're going to be closed. But actually, interestingly, if the snow is more than 7 inches, then it turns out that we're going to be open. And that's because you can see there are 3 examples here, 3 examples in our data where there was more than 7 inches of precipitation, but the school remained open. And maybe that's an error in our data, or maybe that's telling us something about how dedicated we were to being open during those times. Or maybe it was not precipitation that stuck. But you can see that gives us that. We can imagine a scenario if there's less than 3 inches of accumulation, then we can split again and say, okay, well, if there's less than an inch, then we're definitely open. But if there's more than an inch, then, well, it's not quite, if there's more than nothing, right, more than 0.08 inches, then we can ask about, again, amounts. And if it's less than 0.1 of an inch, then we'll close, which is another one of these guys. It's sort of like a weird opposite of what you would think. That's because there doesn't have to be sort of this actual internal consistency to the decisions. And then if it's really windy, if it's not very windy, then we come over here and we're open. But if it's really windy, we go over here. And if the wind is, again, this is one of those weird situations. If the wind is less than 12 miles an hour, then we're going to close. But if it's greater than it, then we're going to open. And so I thought those are sort of weird things. So this tells you what it was able to figure out based upon this is sort of the best guess that it could make about what the decision tree should look like. And I won't get into the details of exactly how it makes that determination, but it's effectively saying which questions can I ask to get to a decision sort of in the most efficient way. And let's actually just go ahead and evaluate that. Here's our same lines from above. And we can see here we have our ROC and precision recall curves. This does actually a better job of sort of matching the prediction versus reality, which is saying like the number of times we said it was closed is roughly around the same as the number of times that it was actually closed, and similar there. So that's to say that this little orange bar is not nothing. But we can see that our precision and recall actually was not very good. Our precision was less than 50%. Our recall was just there. The AUC is not very good. The accuracy doesn't beat the naive. So perhaps not a surprise because this did not look like the thing that I would have guessed for my decisions, but yeah, that didn't work either. So we have one more here. We have this random forest. And what I've done in all of these cases, I've provided links to descriptions of the, or to the documentation for the algorithm. And it will give you a little insight into what's going on. So if you want, you can click through there and read some on exactly what's going on here with a forest of randomized trees. But let's just go ahead and run it and see how it does. And again, we get some weird warnings, probably because we got some weird thing. And we have this precision looking one. It looks like it's great. And you can see here, it made some little predictions about things. ROC looks good, but as we can see here, our F1 score is not that great. And, our recall is not that great. We did just manage to beat with accuracy. We just managed to beat the naive scenario, but we're not passing here because our recall is not better than 0.5. If it had been better than 0.5, we would have passed. That being said, I could go through, I could get a different random draw, and I might pass or I might not pass. And likelihood is that I won't because these are pretty crappy models. I'm going to do a couple random draws here until I get something that's 8. That looks like it might be. But I can go through and I can see that with different training data, the performance is going to look a little different because you're training on different data. So here, for example, our decision tree has changed a good deal. You know, we can see that all changed a good deal. And a very different sort of decision tree. Again, accumulation seems to be the big thing that it thinks is really important. Having an accumulation tends to go towards being closed. You can actually limit, you can do a lot of stuff here. You can sort of limit how many splits, how many nodes things go, so that it's, you know, here I just do something like this, so I can actually just have that sort of biggest. And that actually, this sort of makes sense to me, right? You know, if it's more than 4 inches, then we're going to close. Otherwise, we're going to stay open. But let's see how that does as a prediction. It still doesn't do that great because there was weird outliers where there are a couple times where there was really a lot of precipitation, but we didn't close. So just the data doesn't hold out this sort of naive motion of that's exact idea of that's what happened. In next week, we'll go ahead and we'll do some stuff here, or rather when we're together, we'll do some stuff here with this making predictions, because that's going to tee us up for what we're going to do with the Dewey Cheatham and Howe work. But really, this was, I just sort of wanted to walk you through and talk about how you load the data in and how you interpret some of the stuff coming out of it. All you really need to do on this notebook is you just need to, the only thing you really need to do is to load in this file. And then you'll have to, when there are references specifically to the columns you want, you'll have to make sure those are changed. So for example, in the classifier here, there are a couple times when we mentioned the column closed, you're going to be looking for the column take. And so there are some names there. Obviously, if you're referencing column names to keep, you don't want to make those the columns that you want to keep. But you should, as you will be instructed in the mission below, and we will help do this in class as well, is we will take the data that you prepared for the Dewey, Cheatham, and Howe, that's all nice and square and all numbers, and we'll put this through these predictors as well, through these algorithms, and we'll see if we can make something that's a good prediction. And I'll be really curious to see what this decision tree does. This decision tree is nice for the same reason that a linear regression is nice, or for one of the reasons that a linear regression is nice, is that it's explainable in a sort of intuitive way. So with a linear regression, you can say, oh, this is multiplier, such that this feature, if it gets 2 times as big, then you multiply it by this multiplier, and it's, its multiplier is 4 times that of this other thing. So it's 4 times, it's 4 times the effect on the end number. You can do that with logistic regressions. You can pull out weights on different features. They don't have the same intuitive behavior because of the way that the sigmoid works. But here with but they're descriptible. There's something you can describe, not like a neural network where it's like, oh, you put some stuff in and why is it doing that? I'm not really sure. But a decision tree is nice because you can say, oh, well, this is saying if this is bigger than this, do this, do this. So you can interrogate that logic a little more easily than you could say if it was just this entirely black box. And so for that reason, sometimes you choose to use models like this, even if they're not quite as high performance as other models, because you have an understanding of what's going on. So that's a powerful one there. All right. That being said, you've got your mission below, and it's the same setup as last week. Go ahead, try your hand at it. We'll walk through it together when we have our synchronous meeting, and we'll have some more discussion as well. All right. Good luck.